Okay. Well, hello everybody. Welcome back. This is Mike. You guys, you know me from TikTok and everywhere like that. But here today we have a special guest. His name is Physically Debunked, or Matt, also known as Matt. Um, he's at Oxford. He's a cosmologist, and
I was at Oxford.
was at Oxford. Oh,
just to make it very accurate, I was at Oxford. I did my undergrad and masters at Oxford. I now do a PhD in early universe cosmology at Queen Mary in London.
okay. Yeah, so he'll introduce himself a bit here, and then we'll get into some awesome topics today. Yeah, so go ahead.
Yeah, sure. So I mean, I can say a few things about myself and what I work on, and then what I'm interested in terms of atheism, physics, and all that, and philosophy and all that kind of thing. So what I work on, I trained as a physicist, and now I'm currently undertaking my PhD in early universe cosmology at Queen Mary, University of London. So I'm into my third year now, so I'm towards the end of my PhD. So hopefully, very soon, it may well be Dr. Matt Davies at some point, which would be very exciting. But I've got a lot of work to do before that stage, quite yet. But what I work on is, when I say early universe, I mean very early universe. So the kind of early universe that I work on is the kind of time period where we may know a small amount about what happens during the universe, but there's a huge amount that's unknown, a huge amount still to work out, and there's a lot of things that we don't understand about it. So I work on a particular framework, which is called inflation. And basically, inflation is a period right at the beginning of the known universe, where the universe undergoes a rapid expansion, far faster than the rate at which it's expanding today. Undergoes a rapid expansion, doubling in size every millionth, trillionth of a second, ridiculously small time periods. And then when inflation ended, what's called the hot Big Bang started. And the hot Big Bang is kind of the first moment at which we know almost everything about the evolution of the universe past that point. Okay, the hot Big Bang model, otherwise known as the lambda CDM, lambda cold dark matter model of the universe, or the Big Bang model is what probably most people know it colloquially. It starts at the hot Big Bang, and it basically describes the entire evolution of the universe from 13.7 billion years ago up to the present day. And there's problems with it. There's things that we don't fully understand. There's little bits that there's little tensions that are starting to arise, which hint at the possibility of some new physics. But nobody knows anything better at the moment than the hot Big Bang model. There's nothing else out there which explains the universe as in such a unified way and so accurately as the hot Big Bang model. But obviously, being scientists, being physicists, we're interested in what happened to our universe before the hot Big Bang began. And currently, the leading explanation for, or the leading theory hypothesis as to what happened before the hot Big Bang is this period. There was a period of rapid inflation, expansion, which we call inflation, and this kind of seeded the structure that we now see in the universe today. So we don't know much about it. We basically just say that there's a special field which is a scalar field called an inflaton, and this kind of particle, it may not actually be a particle. It may just behave. There may be lots of things which together behave effectively like a scalar particle. And when you have this kind of thing, the scalar particle in the universe, and it dominates your energy, dominates the amount of matter, dominates the kind of thing you have in the universe, it causes this exponential expansion. So we don't know what it is, but we hypothesize that just before the hot Big Bang, there was this scalar field that drove exponential expansion. And the reason why we hypothesize that it's there is that it explains to some extent a couple of features of the initial conditions needed for the hot Big Bang, that we observe today. So, for example, when we look at the universe on very large scales, what we find is that it's very homogeneous, and also that there are lots of areas in the sky which would never have been able to communicate with each other. So it's a question as to why is the universe basically looks the same everywhere when all these different patches never were in communication with one another. And the other thing that we observe about the universe today is that it's incredibly flat. What flatness means in the case of the universe is a slightly subtle topic, which we can always talk about later. But there's these two things. The universe on large scales is very homogeneous, and it's also very flat. And a question which the hot Big Bang doesn't address is how these initial conditions came about. And so inflation is an attempt to explain why the universe was so flat and so homogeneous at the hot Big Bang. And simply by postulating an exponential expansion just before the hot Big Bang, you actually solve both of these problems, because inflation drives the universe towards being flat, and also it means that actually the patches which look like they were never in communication today were actually in communication, but they just got pushed very far apart by inflation. So that's what I study. So I study this period of inflation, and currently what I work on are two interesting phenomena that could result. So there's not a huge amount of experimental evidence for inflation yet. There's little bits and pieces. So there's something which is called the primordial power spectrum, which is, you can essentially think about as the kind of fingerprint of any model of inflation. Any model of inflation generates a certain primordial power spectrum. This primordial power spectrum then dictates how structure forms. It gives you the seeds of structure that will then, in the later universe, form galaxies and various other things. And we've measured a very small part of the primordial power spectrum. What you can take is the cosmic microwave background, which I hope everyone has seen before. It's that blue and green oval. So we measure the cosmic microwave background, and this gives us a measurement of this primordial power spectrum on a very particular scale. So we know a little bit of it, and inflation correctly predicts what we observe in the CMB for the primordial power spectrum. But at other scales, the nature of this primordial power spectrum is, it could be anything, essentially. We have no constraints on it. We have very few constraints on it. There's all sorts of ways this primordial power spectrum could be. So I study models of inflation that would produce some kind of interesting primordial power spectrum. And what I mean by interesting is that they produce either observable or at least kind of interesting phenomena. So one phenomenon that a theory of inflation could produce is primordial black holes. So most black holes in the universe we know of, every black hole we've ever seen so far, ever detected so far, is a stellar black hole, meaning that it formed from the collapse of a dying star. And we know they're stellar black holes because basically everything above a certain mass, everything above a certain mass is essentially, you know that it's formed from a star. It's a stellar black hole. Anything below that particular mass could not have formed from a star, because in order to get a black hole from a star, you need it to be large enough so that its gravitational pull essentially causes it to collapse and irreversibly pushes it down into a black hole. But it could be the case that there are primordial black holes which didn't form from stars collapsing. They instead formed during this period of inflation. And so they're black holes formed right at the beginning of the universe before there were any stars, and these could have all sorts of different masses. So you could have masses that were below the minimum threshold for a stellar black hole. And so if you ever saw a black hole out there which had a mass smaller than this critical mass, you'd know that it had to have been produced in the early universe and not from a star. And the reason primordial black holes are interesting is because currently in physics we know that there is this quantity called dark matter, and you know people often refer to these things as being a kind of fudge factor. it's kind of unfair to call it a fudge factor because this is something that we study in its own right. It's no different from saying that, say, when we were doing chemistry 200, 300 years ago, it's no different from saying, let's call this thing gas that fills the vacuum in our rooms. We can't see it, but we know some of the effects that it has. Okay, you know you can perform experiments on vacuum chambers and pressure, and you can tell that there is this invisible substance there. It's kind of the same thing with dark matter. We haven't just said it's there to fix our models. We can see its gravitational effects. What we just can't do is we can't actually see it. Hence why it's called dark. But there's plenty of things in the universe that we can't see. There's plenty of things on the Earth that we can't see, but we know they're there. So this dark matter is kind of like when chemists started to realize that there was this state of matter called gas, which filled rooms and is around us everywhere. Dark matter is like gas, but in the universe. It's this substance that we don't know. We don't actually know what it's made of. We don't know what comprises it yet, and we can't detect it with visible light or anything electromagnetic. But we know it's there because of the gravitational effect that it has on the galaxies it's in, and various other things. And so one suggestion has been that the thing I work on, primordial black holes, is one fairly interesting candidate for dark matter. Okay, so there's lots of other theories about dark matter. There's all sorts of theories which postulate that dark matter is some kind of new fundamental particle that we haven't detected before. But what the primordial black hole idea suggests is that you don't have to introduce anything new, potentially. No kinds of new particles, no kinds of weird exotic matter. It may well be that dark matter is just made of lots and lots of these small black holes which were formed during the early universe. And this kind of fits the bill for what we expect from dark matter. Dark matter is something that doesn't interact with electromagnetism, but has a very strong gravitational influence anyway. And that's what a small black hole would do. You have lots of small black holes. Obviously, they're quite massive. They have a large gravitational influence, but you can't see them. You can't detect them with optical telescopes. So that's one potential thing that dark matter could be. And that's what I work on.
Wow, that's amazing. So what you're saying is basically you're working on a paper that says, or you're working on research that basically says that these black holes could be dark matter itself.
Yeah, so there's a lot of research currently into the into this possibility. So,
now,
oh yeah, go on.
Yeah, just to, now, like, how would that be the case? I mean, could these? I'm assuming those primordial black holes would affect each other gravitationally. They would basically merge together to become larger. And how would that work?
They can do in principle if you have enough of them in a small area. It could be the case. So one thing we've noticed about galaxies is that at the center of a galaxy there tends to be one very large kind of supermassive black hole, and then all the rest of the galaxy is then crowded around these very dense, very massive black holes in the center. Now, it could be the case that, for example, the black hole at the center of our galaxy might have started off as several primordial black holes that merged very early on, and then other matter in the universe crowded around these black holes because they have a gravitational pull, and then eventually they grow larger and larger and larger, and the galaxy around them grows larger and larger, and so you get the galaxies with the supermassive black holes in the center that we see today. So this is one particular idea, but it doesn't have to be the case that they kind of keep meeting and merging and combining into bigger black holes. It could be that there are lots of kind of little asteroid-sized black holes spread out around, say, the edges of galaxies, which is roughly where most of the dark matter distribution lies, around the edges of galaxies. So it could be, they don't necessarily have to merge. The idea is just that there's a lot of mass that we can't see, and small black holes very much fit that description.
Right. So that's amazing. Actually, this is quite incredible. So, you said the dark matter pretty much lies on the outskirts of the galaxy.
In
So
general, yes, yeah. The dark matter distribution in galaxies has been mapped, and generally, dark matter tends to hide. Well, I say hide. That's uh, very personified. It tends to dwell on the outsides of galaxies.
and so yeah, so two questions on that. Why would they dwell on the outsides, and also, um, could that mean is that responsible for explaining why stars on the outskirts of galaxies pretty much orbit or revolve around the black hole this at pretty much the same speeds as the inner stars?
So the point of why dark matter was why originally we know that we needed to introduce this quantity is because when you look at how fast galaxies are rotating, there's a relationship between the rotation speed of a galaxy and the amount of matter in it. And what we realized is that for every galaxy we look at, it's rotating far faster than we'd expect if we looked at all the visible matter in it and added that all up. So when you add up all the visible matter in these galaxies, you find that there is not enough matter to explain how quickly the galaxy is rotating. So we introduce what we do very reasonably is to say that, well, perhaps there's a load of matter there that we can't see. It's not a crazy suggestion. There's all sorts of things we've never been able to see. Just because we can't see it doesn't mean it's not there. But the key point is that we can detect it gravitationally, and this basically allows us to locate where in the galaxies dark matter tends to reside. So you can look at the rotation curves for galaxies, and you find that the dark matter distribution seems to be concentrated around the edge of galaxies as opposed to spread out through them. Why this is the case, if dark matter would be primordial black holes, is not something I know a huge amount about. Part of any solution to the dark matter problem would have to explain why, say, these things are at the edges of galaxies rather than in the center. I can't give you an answer that I know to be true, but one suggestion that comes to mind immediately is that it might be the case that there were these little black holes kind of spread out everywhere. Some of them happened to be closer than others, and those ones ended up forming, say, the supermassive black holes in the center of galaxies, and everything clustered around those. But then there's all of these kind of other black holes out there which were never clustered enough, concentrated enough to form their own kind of galactic centers, and so they didn't.
Kind of like our own solar system, where most of the mass is in the center and a lot of it's spread out.
Yeah, exactly.
Angular momentum, things like that, keep things in certain ways. That's amazing. So how would these primordial black holes form in the early universe? I mean, that's my other question.
So how do they form? So basically, in the early universe, you have to kind of combine quantum mechanics and general relativity to an extent. I mean, there's no full marriage of these things yet. Famously, that is the problem of coming up with a quantum theory of gravity. But you can make a stepping stone towards a full theory, which is to have quantum field theory but in curved space-time, which kind of marries quantum theory and general relativity to a very minimal extent. So that's how we model inflation. And what you can do is, because the universe is, say, is much smaller during the period of inflation, you expect the matter distribution in these models to behave quantum mechanically. The scale at which they're at is very small, and so you expect them to have quantum behavior. So what you do is there's a quantity which is called the curvature perturbation, and from general relativity, we know that curvature and kind of how much matter you have in a certain area is basically the same thing. Matter curves space-time. Matter in high concentrations causes curvature. So what we have is this quantity called the curvature perturbation, which basically tells you how much matter or curvature there is at a certain scale relative to the background amount of curvature. So there's a certain kind of background, homogeneous background of matter density. So there's matter spread out fairly evenly, but in certain areas, in certain scales, there may be a little more than the background, or a little less than the background. And so what you do is you take these what are called perturbations, these little differences in the value of the curvature. You quantize them, so you treat them quantum mechanically, and then you evolve them, and eventually, because they start off small, but the universe is expanding at a colossal rate, eventually they end up being very large, and they start behaving classically.
Wow.
Now what happens is that region or scales at which there may be, say, a higher concentration of matter, a higher curvature, these scales, if the perturbation is large enough, if they're more dense by a large enough factor than the surrounding areas, then they will collapse into black holes. If that makes sense.
Yeah. So, okay. So we have now quantum gravity. For people that don't understand, what you're doing there is basically quantizing space-time. So basically, what you're doing is you're making space and time particles, correct?
That's some approaches to quantum gravity are like that. The main aim is just to marry general relativity, theory of the gravitational force, or theory of space-time and gravity, and marry it with quantum mechanics, treating gravity quantum mechanically. Now that can involve, as you say, considering breaking down space and time into something more fundamental, some kind of space-time, whether it's a particle, but something that's the kind of idea behind that. But there are other approaches as well. So, for example, string theory doesn't take that approach. You don't break space and time down into something more fundamental, but you quantize gravity. You have a quantum theory of gravity all the same. You have a quantum description of the gravitational force. But some approaches, for example, say loop covariant quantum gravity or causal set theory, these kinds of theories, their philosophy is to break space and time down into something more fundamental.
Right. Now, how would loop gravity or things like that, how would that affect your idea about primordial black holes being produced in the early universe?
Well, ultimately, what happens in the early universe is dictated in some part by what the correct quantum theory of gravity is, because that theory would describe the universe before the period I study, which is inflation. But during inflation, this description, the description that we use and that we currently know, which is this quantum field theory in curved spacetime, is good enough. It's consistent. It still works at these energies, and so it should be okay. But what, say, a quantum gravity theory might be able to do, so string theory, for example, proposes can do this for inflation, is it can tell you what the particle that actually drives inflation actually is. So at the moment, we just call that particle the inflaton, and we know some of the properties it would have to have. It has to be a scalar particle, unlike an electron, which is a spin half particle, and a photon, which is a spin one particle. A scalar particle is a spin zero particle. So we know its properties, but we don't have a theory of what the inflaton is. Aside from that, we don't understand it like we do the electron and the particles that we're familiar with in the standard model. So what a quantum theory of gravity would hopefully do would be able to tell us, if the inflaton did exist, what particle it was and what theory it came from. So in string theory, one candidate for an inflaton is what's called the axion. So these are scalar particles that you expect to be very abundant in string theory, because they result from the compactification of the extra dimensions in string theory, and so you expect that there's lots of these scalar particles, these axions around. And if there were these lots of axions, it could be the case that these were the kind of thing, were a good candidate for the inflaton that we're looking for. But other quantum theories of gravity would have different suggestions.
Okay, yeah, that's amazing. And now, a lot of people are going to ask, well, what happened before the Big Bang? And of course, this question is something that nobody understands yet. And that not even be the correct question to ask. But potentially, is it possible that this inflaton field is infinite and it essentially permeates all of existence itself, and what you have is many Big Bangs happening, and at all times of the universe? Is that possible?
Yeah. So this is exactly what is what people are referring to when they talk about an eternal inflation picture. So you may have heard of eternal inflation, and it's basically a consequence of inflation itself. Because the way inflation works is that space-time is expanding at this rapid rate everywhere until a certain particle fluctuates a little bit and causes the end of inflation. Now, if this fluctuation occurs, then inflation ends, and you get the hot Big Bang, and you get a universe such as ours. But the nature of this fluctuation is that it doesn't happen everywhere all at once and at one time. It's not the case that there's a little fluctuation and then everywhere stops inflating and everywhere becomes our universe and the hot Big Bang starts. What happens is that this fluctuation occurs in a certain local region, and that region stops inflating and a hot Big Bang starts in that region. So our universe would be a certain region in a much larger inflating space-time where lots of it is still inflating. So there'll be more beyond our universe, and where this much larger space-time comes from and would be another question. But this is this kind of bubble universe picture where the mathematics of inflation tell us that it's not the case that you just have inflation ending and it happens everywhere. No, you have one very large inflating space-time, and at lots of different places in the space-time, this fluctuation may occur, end inflation, and start a Big Bang, and essentially start a universe such as our own. And you can imagine if one happens here, then immediately all the space around it is actually inflating larger than the little universe itself. So the little universe starts growing and forms its own little observable universe, but all the space around it is expanding still at a much faster rate. And so all of these bubble universes are completely disconnected. The space between them just inflates exponentially, and there's no way of communicating between these things. So this is the little bubble kind of island universe picture where lots of different universes begin, in a sense, when inflation ends in their local region. But all of these little bubbles are separate universes that are completely causally disconnected from one another. That's what follows from the maths of inflation. So, if inflation correctly describes our early universe, then one has to just accept that mathematically a consequence of this is that we live in a much larger inflating space-time, and we're just one universe of possibly many. Where this inflationary universe, where this much larger inflating space-time comes from, and whether it can actually inflate eternally, is an open question. There's not. The way to answer that question would be having a proper theory of quantum gravity, or at least a more fundamental theory of gravity that we could apply to cosmology. But that's what the current equations say. Is it sensible? Is it actually real? Don't really know. It's a case of extrapolating a theory and seeing what it says before the time period that we're interested in. So we don't really know if it's sensible, but that's what the math says. And if the maths is correctly predicting the things that you actually see in the universe, well, then that gives some weight to what it's saying about the things that you can't observe.
Right. Now, I want to touch on this recent idea called the second dark Big Bang. Essentially, what that says is because dark matter isn't required for the early universe, you can have the Big Bang occur, the regular one that we know of, and then a second Big Bang occur where there's like this propagation of dark energy or dark matter into the universe, and that's where it kind of happened. What do you think about that?
It's not something I've seen a lot of. There's been plenty of talk before about kind of mirror universes, where the Big Bang wasn't an event that just produced our universe, but there's kind of like an antimatter universe or a mirror universe kind of out the back end of our Big Bang. So I've heard about these kinds of ideas before, and like any idea, the point of it is to try and solve a problem in current cosmology. Whether it's a sensible idea, it depends on how convincing you think the philosophy of the idea is, for a start. Do you think you need this extra process to generate dark matter? Do you think that there actually is an antimatter problem and that this is the way to solve it? And the other side of the coin is that if it's a good idea, then there should be some kind of evidence for it, some kind of observational, testable evidence that can decide whether this thing is actually there or not. So I haven't heard specifically about this second dark matter Big Bang. It could be the case. I don't know enough about it to say rule it out, but it's about, at the end of the day, it's about comparing theories. And so for one theory could be that your dark matter is primordial black holes and produced during that. And that's quite an attractive theory because we're not adding anything new. We're not adding a new kind of process. We're not adding a new kind of matter. This would be a mechanism within currently understood physics that would be capable of producing a dark matter-like thing. But it could very well be the case that at some point we actually rule out that there could have been primordial black holes produced during the early universe. So in order for these black holes to actually be produced, you need a really colossal enhancement of the primordial power spectrum at smaller scales. And this enhancement is, in some senses, quite fine-tuned, very dramatic. And it may be the case that you don't buy that inflation is going to do something that dramatic, do something that dramatic that powerful in the early universe. So some people aren't convinced by the primordial black hole idea. Others think it's a good idea. Other people work on dark matter being some kind of particle from beyond the standard model. This second dark Big Bang is maybe another idea that's very recently come out. Not a bad idea, but something to work out the consequences of, work through, see what it predicts, see if it contradicts anything we've already observed. But yeah, you're adding in a new process essentially, and you adding a process is a cost, and you hope that the benefit that you get out of it outweighs the original cost. And good theories do that, and bad theories end up falling short of it. But it's always interesting to investigate all sorts of ideas, because at the moment there's all sorts of ideas in cosmology to fix various mysteries and puzzles in it, and none of them are really particularly convincing at the moment.
Right. And in science, we operate pretty much on Occam's razor, right? Like the most explanatory power with the least amount of processes and mechanisms. That's what wins you in science.
Exactly. Yes.
Yeah. So I want to talk about another recent thing that happened was people were talking about the James Webb Telescope discovering galaxies in the early universe where they appear to be larger than we would expect them to be. And a lot of people are saying, well, that means the Big Bang's debunked, or it never happened, or we have to rewrite all the textbooks. Go ahead.
I mean, it's rather silly, really, because if there were these kinds of galaxies to debunk the Big Bang, there'd be far more of them, and they'd be far more obvious than the current suggestions. What would rule out the Big Bang instantly is if you could observe a universe a fully formed universe that dates to pre 13.7 billion years. If you can find something like that, and if you don't believe in the Big Bang Theory, then they really must be out there. Then the James Webb should be able to see all sorts of these. Should be able to see loads of these kinds of galaxies if they're out there. That's not what we're finding. What we're finding is galaxies which seem to be larger than we would have expected in the early universe. They're not older than the universe. They just seem to be a bit larger than we would have expected based on our current understanding of galaxy formation. Now, there's several explanations that could be the case. There's several ideas that could explain why we've observed this galaxy and why it appears to be larger than we expect. It could be the case that our expectations are wrong. It could be the case that our current understanding of galaxy formation is lacking some fundamental principle or lacking some fundamental idea. And if the more we study these early galaxies, it might be very clear as to what we're missing, and then these large galaxies won't be such of a conundrum. Another possibility is that the measurements aren't quite right. It could be the case that every measurement in physics, in observational physics, comes with an error. It could be the case that there are still large error bars on these measurements, and they may not be quite as big as we think they are. They may also not be quite as young as we think they are. If these galaxies were older than our current measurements suggest, then there's less of a puzzle as to why they're large, because they've had a longer time to develop. And there's also the problem of, when you observe a galaxy, how do you know that it's a large galaxy that's very, very old and very, very far away? Sorry, a large galaxy that's very far away, as opposed to a small galaxy that's much closer to you. And so it could be the case that some of these are ones where actually it's very difficult to tell whether it's a small and very close galaxy or a far and very large galaxy, because they, in some senses, in some lights, in some angles, they look the same. So what you should take every suggestion of these galaxies being too big and that they rule out the Big Bang or rule out our ideas about the early universe. You should take them with a pinch of salt. It all depends on, can we trust these measurements? And if we can trust these measurements, is there just something that we're missing in our theory that if we just add it, it solves the problem fairly naturally, and we don't need to resort to anything more drastic than that? And at the moment, with the stuff that the James Webb Telescope has found, is generally what we would have wanted it to found. It's found some interesting new puzzles, some interesting new challenges to our current ideas of galaxy formation in the early universe, and it's going to teach us more about that. And either we learn more and fix these inconsistencies, or it may well turn out that there is something that is quite wrong with our current theories, in which case it will lead us to new physics that we're trying to get to. We know that there's new physics out there. We know that there's plenty of open problems and puzzles in the current standard model of physics and the standard model of cosmology, and we really just want to work out how exactly to solve these problems. And JWST will go some way, perhaps, to doing this. But if it was actually going to rule out the general idea of the Big Bang Theory, it would be so straightforward if it was wrong. You just need to find a galaxy that's far older than 13 not even far older, that's just older by a bit than 13.7 billion years. And if the Big Bang Theory was wrong and something like the steady state model of the universe was correct, well, then you'd expect to see very old galaxies as far as you look. And if they were there, which it's very obvious at this point that they're not, James Webb would almost certainly have found them already.
Right.
It's not about ruling out the Big Bang. It's about trying to solve the problems that we know are there in the Big Bang Theory.
Right. People just want to poke holes in things because they want to, it fits their agenda. Uh,
Mm.
yeah, but in science, we don't operate that way. We operate based on what the evidence shows and how we explain the problem, the issues, like you just said. Yeah. So I also wanted to talk about essentially. Well, I did want to talk about your philosophy of how things work, but say that for last. Um, when it comes to the Big Bang, I know in the early universe there was something called supersymmetry, where all the laws of physics were basically conjoined. Is that is that accurate?
It's the rough kind of idea. So I mean, supersymmetry is has been a topic that's been explored for quite some time now. It was proposed 50 years ago or so, possibly slightly longer. And the reason it was proposed was it was basically an investigation into how symmetric can you make particle physics. So uh, we know that the standard model of particle physics is not complete. There's more to the story. There's almost certainly more particles out there, and there's puzzles, there's observations that currently contradict the standard model. For example, in the standard model, these tiny little neutral particles called neutrinos, in the standard model, they have no mass, and there's no way of giving them mass in the standard model. So we know that there must be some more particle physics beyond the standard model that gives the neutrinos their very tiny mass. Now, people have been working on theories of extending the standard model for so long, and one of the early theories was supersymmetry, and this is the idea where you add an extra symmetry into the standard model, into the model of particle physics. In the standard model of particle physics, you already have various symmetries in there. Each kind of force is associated with a certain symmetry. Electromagnetism has what's called a U1 symmetry, which, unless you're familiar with mathematics, won't mean a lot. But let's just say each of the forces has its own symmetry. Now, what supersymmetry suggests is that, or the question supersymmetry asked is, how symmetric can we make particle physics? And one of the symmetries that they found that they could introduce was a symmetry between fermions and bosons. So fermions are particles like electrons and quarks, things that make up the matter that we're pretty familiar with. They make up the kind of solid matter in a sense. And then there's the bosons, which are otherwise known as the force carriers. They carry forces, they propagate forces. So for each different force, you have a corresponding boson which propagates that, which transmits that force. So for light, for electromagnetism, you have the photon. For the strong nuclear force, you have the gluon. And then you have the W and Z bosons for the weak force, and there's the hypothetical graviton for gravity, which would transmit the gravitational force. Now, the standard model is fairly ugly. It's a collection of 20 or so particles, and it's not really. There are some symmetries there, but it's really quite an ugly theory. So what supersymmetry attempts to do is to make it more symmetric by postulating that there is a symmetry that exchanges these bosons and fermions. And so what supersymmetry suggests is that every particle we've observed so far has a corresponding superparticle, a superpartner, which we haven't yet observed, and is its symmetric particle. So it's quite amusing because all of them have very ridiculous names that they form basically by putting an S in front of the name of every current particle. So instead of quarks, or rather, so every quark, which is a fermion, has a superparticle, a superpartner, which is called a squark and is a boson. And you get all sorts of ridiculous names. There's the sup quark, there's down squark, the electrons are in a group known as the leptons, and so you'd have selectrons and sleptons. And I mean, they haven't been very imaginative with these names, but there are so many particles to name that you can maybe forgive particle physicists. But I mean, they sound stupid, which doesn't help, I think, with taking the theory seriously.
Yeah.
But mathematically, this is a very interesting and well-defined idea. To postulate this symmetry between fermions and bosons gives you a very mathematically pretty theory. And what you were saying in terms of it unifies the forces, what it would do is it would unify a lot of the particles and forces that we currently know of into something more symmetric, more what feels more natural in a sense. So this is an idea that's been around for quite a while, and one of the original aims of, say, the Large Hadron Collider was to try and detect these superparticles. And what you expect, the reason you wouldn't have expected to already have seen a superparticle is because they all have masses much larger than their corresponding their corresponding partners, which are the particles we've already observed. So there was some hope that the energies at the Large Hadron Collider would have been high enough to start detecting some of these superparticles. We haven't found any, and now the question remains, do they exist somewhere at some high enough energy that we haven't reached yet, or do they just not exist at all? And so at the moment there is no experimental evidence for supersymmetry, but there are problems in the current standard model of particle physics that demand some particle physics beyond the standard model. It could be the case that supersymmetry does exist and would explain the various problems in the standard model at the moment. Or perhaps not. And it may be some other theory, and we need some other idea to solve these problems. But supersymmetry is something that has been proposed for a long time, and in a sense, it can stay alive because it doesn't necessarily tell you what energy to definitely expect these superparticles to appear at. But the higher we ramp up the energy, and if we keep not finding them, it becomes more and more suggestive that we should abandon this theory. But as you were saying, supersymmetry, if it existed, would be important in the early universe, because the whole point of these theories, these extensions to the standard model, is that they only apply at higher energies. And as you go closer and closer to the Big Bang, as you go earlier and earlier in the universe, the energy density in the universe gets higher and higher and higher. And so at some point, the energy density in the universe is high enough that these particles exist naturally, and obviously they'd have a role to play. And perhaps it's the case that the inflaton that we hypothesize in inflation is maybe a superparticle of some kind, and that during inflation, supersymmetry or the energies that inflation occurs at are high enough that supersymmetry applies, and so there's some supersymmetric particle which is responsible for inflation. But it's a fascinating idea, mathematically beautiful. It's really interesting to study. Whether it actually exists becomes more and more doubtful at the moment. But it's not ruled out, but one should be quite sober about the fact that we haven't already found it.
Right. And yeah, that's amazing. And one last thing, I made a video recently in my TikTok about the Higgs field in mass, where we get mass from. And we know that our mass comes from our protons and neutrons, electrons, although very small. The point is that if we go into a proton, there is basically quarks or gluons, in case of the neutron. And when we try to account for the mass inside of these particles, there's not enough to account for just the particle themselves individually. There's not enough mass there to account for how much we observe for the particle. So there's got to be something about the quarks and gluons that gives us our mass. And because the Higgs field only accounts for about 1% to 2% of our mass, right? So the idea is that our mass comes from the binding forces between those gluons and quarks. So I just wanted to ask you, like, what do you think about that, and what does that say about the rest of physics?
Well, I think that's just the currently understood. That this is an interesting thing where naively there isn't enough mass just from the protons and the quarks themselves to actually make up the mass of a proton. But this is the story from the 20th century, really, the mid to late 20th century, where we started developing quantum field theories. So quantum theory before then, there's not enough mass in say quarks to account for the mass that a proton has. You develop quantum field theories. You develop the most, I guess, advanced quantum field theory at the moment is called quantum chromodynamics, and it describes the strong interactions of the quarks and gluons inside protons and neutrons. And in the framework of quantum chromodynamics, yes, you see that the extra energy density comes from the bindings of the quarks and the gluons, and that accounts for the energy, and energy is in some sense mass, and so it is all accounted for. So it's not something that hints towards, say, that there needs to be extra physics. It was an interesting problem, and as far as I'm aware, quantum chromodynamics tells us the answer, which is that there's a lot of this. The energy here is contained within the binding of gluons and quarks.
Yeah, it's just mind-boggling. That idea though, like we tend to think of matter as like this tangible substance, but on a quantum level, there's something way different going on. I mean, how would those forces give us mass? I guess like the relationship between energy and mass is mind-boggling to grasp, right?
Yes, yeah. You suddenly lose all grip on reality when you start working at the level of quantum field theory. The best picture I can think of describing what we currently understand about what life is like down at the quantum level is that you can think of, there's no matter really anymore. There's no kind of hard little lumps of Lego down at the fundamental scale. There's no little hard billiard balls bouncing around. It's more like the fundamental ingredient in quantum field theory is a field. It's a continuous field across all space and time. And what matter is, or rather, so you can think of this field as being, say, like a fluid that fills all of space and time. And what matter is are waves within this fluid. So when you get a particle, it's kind of like a little wave packet, a little wave that can propagate through this fluid. So in a sense, particles aren't actually their own things. They're actually structures that form within this fluid, and the fluid is actually, in a sense, what's there. But I mean, this is quantum field theory at the moment, and it can't be the full story, because what quantum field theory assumes is that you have a space-time on which these fields are defined, and obviously, space-time is something we want to understand at a quantum level, and so if we're trying to quantize space-time, it's no longer the case. That's not exactly how a field will be defined anymore. If you're breaking down space-time into smaller bits, then you have to rethink what a field is spread out through space-time. But currently, this is the nicest picture, I think, to have of what's going on at the level of quantum field theory. You have stable structures, which are little waves kind of moving through, and these are particles, and there's other waves that travel between particles and transmit forces between them. And then there's also this other idea in the popular physics, which is virtual particles. And the way you can think of these is that they're not quite proper waves, but they're tiny little chaotic ripples in the fluid that disappear before they travel any significant distance, and so only affect things very, very locally. All you see are these long-lived, stable structures, these waves in the fluid, and all these virtual particles are just little fluctuations all around the place.
Wow, that's mind-boggling. Now, yeah, what do you think? I'm going to go back to black holes for a second. First, I want to get your opinion on EPR equals, is it EDR or something? I don't know.
Yeah.
Wormholes being essentially, quantum entanglement. I also want to get your opinion on like what happens inside of a black hole. What is there something beyond the black hole? Is there another universe? Are we in a black hole right now? Just real quick.
Yeah, no. So this idea of we all every physicist would like to know what happens in a black hole. And the reason we don't know what happens in a black hole is because we don't have a quantum theory of gravity. Inside a black hole, the interaction between gravity and everything else becomes so strong that the only way you're going to be able to describe it is with a more fundamental theory of quantum gravity. In general relativity, all it tells you is that at the center of a black hole, the curvature blows up. And so what that means is that as with singularities that we've encountered throughout the history of physics, what that suggests is not that there's actually a point of infinite density and infinite mass crushed down into an infinitely small space. It tells us that our theory is not capable of describing what's going on there. You need a better theory. So what actually happens within a black hole is totally totally determined by what a quantum theory of gravity would say happens at a black hole. That's not necessarily all we can say about that, because what we can do is mathematically we can study the structure of space-time and general relativity around a black hole and around different kinds of black hole. And what the mathematics tells us is that even though at the very center of a black hole, the curvature goes to infinity, and so you definitely can't describe what's happening physically anymore with your theory. You can kind of extend beyond that point. Mathematically, it makes absolute sense to go beyond that central singularity and extend your coordinates through the black hole, in a sense. Mathematically, this is totally fine. And what you end up with is basically a space-time which is totally fine everywhere except at the actual center, the singularity of the black hole. Now, it might be the case that actually extending our coordinates beyond the black hole is a completely
impossible.
Is not actually well defined. Is not possible physically. It may just be theoretical nonsense. But if you trust that on either side of this singularity where general relativity doesn't apply, that general relativity does apply once you've got far enough away from the singularity, which is making everything too energetic, too strongly gravitating. Well, what actually happens is what you can draw what are called Penrose diagrams. And these are kind of diagrams that depict how what the structure of space-time is around the black hole and on a global scale. And what happens is that if you try and draw these diagrams for black holes, mathematically what you can do is you can extend your coordinates through the singularity and into a disconnected separate space-time that extends beyond the black hole. And so this is the idea. This is basically the origin of the idea that black holes may well lead to other things. That if you could travel past the singularity, there's actually a whole space-time, a whole universe beyond the singularity that you can go across into. And what you see, if you study the mathematics of how the space-time behaves, you see the opposite of what would happen for a black hole in our universe. For a black hole in our universe, every trajectory that crosses the event horizon ends up going straight into the singularity and gets sucked in. On the other side, if you continue the coordinates, the opposite happens. Every trajectory begins at the singularity, but forces you out of the black hole and out into a wider space-time. And so there's a very neat idea that inside each black hole is actually a universe. That the formation of a black hole in one universe is the Big Bang of the next universe. So you can think of every universe kind of has roots that lead to other new universes, and other new universes, new space-times are forming inside black holes. So mathematically, there's some interesting motivation for this. Obviously, there's obviously no direct observable evidence for this. But what you can say is that obviously we have observable evidence for general relativity, and we trust general relativity quite a lot. And if the mathematics of general relativity suggests that this is what's going on past through a singularity or a black hole, then observations of general relativity in our universe and confirming general relativity offers some weight to the claims that general relativity makes that we can't observe. And so this is why people take these ideas seriously. At the end of the day, it comes down to whatever quantum gravity says happens at the singularity and whether you can go beyond it. But with our current theories, we can say that you can extend past a singularity, and there's a white hole, there's a separate space-time on the other side, and you can also and wormholes and all these other things are perfectly mathematically well defined in general relativity, but we have no way of observing the inside of a black hole at the moment, and theoretically, you're crossing a singularity, and so that's not necessarily a sensible thing to do, even if you can do it mathematically.
Right. It's mind-bending. All right. So yeah, last question. So I'm an atheist. I don't believe in a God.
Yeah.
I know you're. I would guess you're an atheist as well.
I am indeed, yes.
From what I've seen on TikTok. But I find it, because a lot of people who are in our positions, in our shoes, we feel like there's nothing for us to feel hopeful about or to feel spiritual about, right? To feel good about. So we often find ourselves looking for something that gives us purpose or meaning beyond religion, because we know religion is nonsense, but we want something. So where do you find your, like, even from your perspective, right, as a PhD candidate physicist, like, how do you find purpose and meaning in your life, and what's your philosophy of life, and what's your what do you think?
Yeah, well, I mean, it's at the end of the day, it's one of the most important questions. And yeah, as being an atheist, you don't have the kind of obvious answer where the religion dictates to you it tells you what the meaning of life is. It tells you what to aim for. It makes it very clear what that is. No, once you go past religion, what's on the other side? And to me, it's a combination of two things. It's enjoying my life as it is, and living life how in what I think is the best way possible. And that's the very parochial side of it. That's the small scale. On a day-to-day basis, I just want to enjoy what I'm doing each day and do things that I find interesting, spend time with the people that I love, and have as many fun experiences as possible. On the other side, if you're thinking about, say, what it all means on a grand universal scale, well, I personally just take refuge in the fact that we don't know. Ultimately, what we found with physics and cosmology and science is that the universe seems to get larger and larger the more we investigate it. And there's so many things that we don't understand, and we've gone from thinking that there were no stars outside our galaxy and not really even knowing what galaxies were, to thinking that there may well be disconnected universes, trillions of universes, and we're just one little universe in a much bigger multiverse, and that there may be universes inside black holes, and where do the laws of physics come from? There's the universe has only been getting bigger and bigger since we started investigating it. And that also means that the mysteries have actually just been bigger and bigger. Every time you solve a mystery, you get a new one, and it's more fundamental. And I take refuge in the fact that in this massive, wide, and mysterious universe, there's so much we don't know, and there's so many interesting ideas. And if any one of them were to be the case, what a fascinating world we live in. But while we don't know what is the case, who knows what it could be? I mean, the idea that the universe is a simulation isn't crazy if you consider certain pieces of evidence. The idea that we live in a black hole isn't crazy. The idea that there's a much wider multiverse has decent motivations. The idea that there are lots of parallel quantum universes in a many worlds interpretation of quantum mechanics is an interesting and sensible idea. And if something like the many worlds interpretation of quantum mechanics was true, that would completely change our perspective of life, the universe, and everything forever. So no, I take refuge in enjoying my day-to-day life on a very day-to-day basis, on a very small scale, and also just being fascinated by the mysteries of the universe around us and all the interesting things that our universe could be.
Yeah, it's a fantastic answer. I would say that for me, throughout my life, learning was the biggest thing for me. From when I was 10 years old, looking on Discovery Channel or Science Channel, just understanding these new things, these ideas that changed the way I saw existence, saw my life. And the fact that this happens every day or frequently in science is a tool that allows us to peer deeper into the universe and peer deeper into our existence. Go places where you've never gone before. So that to me is why I think learning in scientific literacy is really what makes me happy, and it gives me purpose and meaning.
Agreed. I've always just had this love of learning, and that's why I'm a physicist. At the end of the day, I just like to know more because I think the universe is fascinating already, and there's so many open-ended questions still that the room is there for it just to become even more fascinating and even more mind-boggling. And I'm excited to see where it goes.
Right. And the fact that we're here for these mere 60, 70, 80 years, able to comprehend this, whatever it is, this place, to me is fascinating because there's nobody dictating how I'm supposed to live my life, because there's no agency determining the universe, but because we just are. And we exist here and we're just learning as we go. And there's no trajectory necessarily as to where we're going to be, but we are just here to enjoy and understand it. And that's and that's really all we have. We should end it now, but appreciate you being on.
No, thanks for having me on again. I've enjoyed it.
Yeah, I really hope that you get your PhD soon. You deserve it.
Thank you very much.
By the way, when would that happen? This year?
So it's 3.5 years is how long the funding lasts. So I've done 2.5 years, but at this point, so I'm in my third year. So there's about a year to go. Funding may well need to be extended if I need more time to complete some of the research. But hopefully within the next 12 to 18 months is probably when I may well be able to call myself a doctor, which would be very exciting.
It will be, man. You definitely deserve it. I appreciate the reason why I've had other STEM people here on my channel. The reason why it's because you guys literally are the ones that change the world and make it a better place. You guys literally do. I admire STEM people so much because we need more of you guys in this world.
Well, thank you.
So that's why I promote you, and I think that I'm always going to, promote your work because what you're doing is good.
Well, thank you very much, and just as important are the people like you who take a very active interest in actually learning these things, because so many people sadly have their own agendas and look up a few facts, fit them into their narrative, and go no further. But it's great to have people like you who are so interested in actually speaking to people who work on it and being very open about the things we're saying.
Of course, man. Yeah. So thanks for being here again. I think that's all.
Thank you very much.
You guys for watching. Go follow him. Go find him on Physically Debunked on YouTube or TikTok. He's always there. And that's it. Appreciate it being here. Have a good day, everybody. Enjoy.